All right, so when we left on Wednesday, I left you with this kind of open-ended big question. And the question was, based on what we know about electrons, based on what we know about atomic orbitals, and what we just kind of brought in with valence bond theory, the idea that in order for electrons to be shared, we have to have orbitals overlapping on each other. And so we could pinpoint that the s orbitals, because they're spherical, would overlap nicely. The p orbitals that are in that horizontal axis would overlap nicely. But the ones in the vertical axis and the ones in the depth axis can't get close enough to each other to bond on their own. They're great for pi bonding, but they're not good for anything other than that. They're not going to form a sigma bond, and therefore they're not going to form any kind of bond on their own. And yet, we have seen example after example of molecules that have 4 covalent bonds, 5 covalent bonds, 6 covalent bonds. How's that possible? The answer to that question comes from a concept that we have yet not discussed, something called hybridization. I think we can probably recognize at this point that our current understanding of electrons and electron location is insufficient to answer the question that was posed at the end of Wednesday. What we get into instead are the use of what are called hybrid molecules. That is, molecules that integrate atomic orbitals in such a way to minimize repulsion and give us those bond angles, those orbitals that are capable of interacting in that internuclear axis to give us those sigma bonds. And so I want to highlight something in particular in this definition. Using mixtures of atomic orbitals to minimize electron pair repulsion. If that sounds familiar, remember, this was the very heart of VSEPR theory. The EPR in VSEPR are electron pair repulsions. So VSEPR theory covered the what? Covered the what is this question? What molecular shapes form when we have bonding of this kind? Hybridization answers the how or the why question. How do we get the molecular shapes that we described? Why do they form in the bond angles that they do? Hybridization is the answer to both of those questions. What we get are things called hybrid orbitals. Hybrid orbitals are the mixtures of s orbitals, p orbitals, and in some cases, d orbitals as well. These hybrid orbitals come in sets. Every shape, every electron domain geometry that we discussed has its own unique set of hybrid orbitals. And the formation of those is 1-to-1. meaning every hybrid orbital comes from an atomic orbital. So if I have a steric number of 5, I'm going to have 5 hybrid orbitals. They are going to be derived from 5 atomic orbitals. If I have a steric number of 3, I'm going to need 3 hybrid orbitals, which are derived from 3 atomic orbitals. It's a 1-to-1 ratio. My steric number, my hybrid orbitals, and the atomic orbitals that they came from all speak in terms of the same language. They're all the same number of orbitals. And the orbitals that we combine typically come from a lowest energy to highest energy kind of orientation, which means s orbitals, because they are the lowest in energy, are always going to get integrated first. P orbitals will always be integrated second. D orbitals, if necessary, would get integrated last if needed. So to help illustrate this a little bit better, we're going to bring out a couple of examples and show the different types of hybridization that exist for the different types of molecular shapes. So in total, we're going to look at 5 different examples because there are 5 base domain shapes that we talked about. For the first, I want you to consider beryllium. Now, based upon our definition of orbital overlap, we need to have orbitals with single electrons in them so that that one electron can be shared with the one electron in the other atom to give us that covalent bond. If we look at this orbital notation for beryllium, however, we see that we have none of those unpaired electrons. Both of the electrons in the valence shell are paired. They're both in the 2s orbital. So from an atomic standpoint, beryllium would be pretty lousy at making covalent bonds. Once we throw hybridization in, however, what we can see is that those 2 valence electrons, if we were able to separate them somehow, would be capable of making 2 covalent bonds. And the means by which they do it, hybridization, they take an s orbital and a p orbital. They combine them together to create 2 hybrid orbitals. The hybrid orbitals are called sp hybrid orbitals because they are derived from a single s orbital and a single p orbital. So sp becomes the designation there. And when I put the 2 hybrid orbitals together, what I get is this arrangement here in 3-dimensional space, where 1 electron can sit in this orbital and 1 electron can sit in this orbital, and now both are capable of going out and making covalent bonds. What I want you to look at here is look at this orientation. Those 2 orbital lobes are 180 degrees apart. The shape we would call linear. And so in this case, if we had a steric number of 2, it would give us sp hybridization as a result. We've already covered this with VSEPR theory. A steric number of 2 gives us a linear shape. How does it come up to that linear shape? It comes by it through sp hybridization. So all of the pieces fit together. We're not talking about separate theories here. Again, reiterating, VSEPR theory gives us the what, tells us what the steric numbers are, tells us what the shapes are, gives us the bond angles. Hybridization tells us how we got to those shapes in the first place, through the blending together of those orbitals. So they're not separate theories, they're complementary pieces. One's answering the question of what, one's answering the question of how. Complementary parts. So in action here, we can see that because of the arrangement of those beryllium, because of the hybridization of the beryllium, beryllium is capable of going out and forming covalent bonds and can do so with other atoms, in this case fluorine, through the direct overlap of these hybrid orbitals with the atomic orbitals of each fluorine atom. We get direct overlap, we get 2 sigma bonds as a result. So how would it look from the perspective of our orbital notation, or orbital notation electron configuration? You recall that initially we had 1s2, 2s2, 2p empty. Hybridization sticks right in between S and P in terms of energy. Integrating that p orbital into the s is going to raise the energy of the s. Integrating the p or the s orbital into the p sublevel would lower the energy of the p sublevel. So they exist right in between the two. But in going through that hybridization process, we can see that we now have the capability of doing that direct overlap bonding. All right, any questions here with sp hybridization before we move on? Ben?
Do you have to label the energy level of the SP?
Yes, technically this would be the second energy level. This would be 2sp because both of the sets of atomic orbitals came from the second energy level. That probably won't come up anywhere, but yes. Yes, we are talking about the second energy level there. Other questions? Okay, let's look at another example. This time we're going to look at boron. Now, in boron, we had 1s2, 2s2, 2p1. So again, you would look at this and say, based upon these results, boron can only form the one chemical bond. This one unpaired electron in the p sublevel would be the thing that boron could use to do its bonding. However, With hybridization, what we can do effectively is in combining this set of orbitals, an s orbital and two of the p orbitals, 3 orbitals in total for 3 electrons trying to bond, we could separate all 3 of them into these hybrid orbitals. These hybrid orbitals would not bear the designation sp because there are more than one of those p orbitals that have been integrated. They would be called sp2. Again, the p2 there, meaning that we've integrated 2 of the p orbitals from that p sublevel with the s, now giving us 3 in total. When I put these 3 lobes together, I get this configuration. This configuration has bond angles of 120 degrees. We know it affectionately as trigonal planar. And so boron can put 1 electron in each of those 3 lobes, which will allow the boron to go out and make its 3 bonds. All right, let's go one step further. Carbon. If you recall carbon's electron configuration, 1s2, 2s2, 2p2. Based on the atomic configuration, I only have 2 unpaired electrons. I could only make 2 bonds. But the problem there is only one of those bonds could actually be a sigma bond. Because recall, only one of the p orbitals is actually capable of doing the direct overlap. The other 2 can only exist in parallel. But if I integrate all of my valence sublevels, that is my s orbital and all 3 of my p orbitals, my configuration would give me 4 hybrid orbitals, allowing those 4 electrons to separate completely from each other, giving me the capability of making 4 covalent bonds. And so my hybridization occurs, I get 4 lobes, which when I add them all together, give me this shape where all of the atomic or all of the hybrid orbitals are 109.5 degrees apart. We call that tetrahedral. All right, any questions with either of these 2 orbital sets? Go ahead, Aniki.
Okay, so I'm kind of confused when it's like a repeat of sp3 orbital, right?
Yes.
Because like I don't really understand how you like how that even possible when there's like 2 here and is this
Okay, so the advantage that we have here is that all 4 of these orbitals are in the same energy level.
Okay.
The s orbital and the 3p orbitals, the p sublevel, they're all in the second energy level. And so relatively speaking, they all have relatively close energies to each other. Now, granted, some are going to have a little bit more, the p sublevel is a little bit higher in energy than the s. But they're all in the same energy level. And so when we blend them together to make these hybrid orbitals, it's really not that big of a deal to put them together because they are that close together in energy. And what it allows them to do is we go from, keep in mind, these orbitals, so this is a spherical, the s is spherical. But if I put the 3 p's together, I would have an x, a y, and a z. 3 sets of orbitals all in the cardinal directions. That wouldn't yield anything close to electron repulsion. These guys would all be 90 degrees apart from each other. So even if they could interact in a face-to-face kind of manner, they would still be at 90 degrees apart from each other instead of 109.5. The hybridization helps us to explain why we get that electron pair minimization in terms of repulsion, why we are able to push those boundaries out to 120 degrees instead of 90 degrees, out to 109.5 degrees instead of 90 degrees. And as we're about to see, how we can even fathom how something could go hypervalent and go beyond the octet rule. Because right now, all we've done is we've stayed in the confines of the octet rule. If I have 4 hybrid orbitals, each one carrying 2 electrons, that's 8 electrons in total. That is the very definition of the octet rule. How do I go beyond that? How do I get something like sulfur hexafluoride, which would have 6 bonds in it? Or something like what we saw with the triiodide ion, where we've got 10 electrons around that center iodine. Any other questions? So we're ready to move on and talk about expanded octets. So again, thus far, all that we've been able to see and do has focused on staying within the confines of the octet rule, staying within the confines of what we consider the valence shell of a molecule. That is that outermost energy level, the S and the P sublevels in particular in that outer energy level. If we're gonna go hypervalent, we have no choice but to integrate d orbitals into that discussion. That's the only other place where we can stash extra electrons. Which brings us back to the point that we made way back in chapter 4 about when is it okay to break the octet rule. You have to have d orbitals available, which means that you have to have an element that is in the 3rd energy level or below. So all the examples we've done thus far, none of them can apply to this kind of an argument. Beryllium, boron, carbon, and any of the others that are there, we focused on those 3 in particular. All of them are in the 2nd energy level. None of them have d orbitals in that 2nd energy level to pull from. But starting with sodium, now we have the 3rd energy level, and the 3rd energy level has d orbitals, has a d sublevel. Now, Most of the elements in the third energy level won't ever use that D sublevel. There is a significant gap between the 3p and the 3d sublevels in terms of energy. However, if circumstances dictate, and usually where we find them dictating is in the integration of molecules that have high electronegative outer elements, things like halogens. That's where we tend to see this the most often. Then those circumstances are a little bit more forgiving in terms of that energy gap that would need to be overcome. This is the place where we deviate the most from your textbook. Your textbook will not talk to you at all about either of these two hybrid orbital shapes. And their argument and their reasoning is that because in reality, these hybrid orbitals don't quite exist exactly the way that we're talking about them. I'm giving you a picture that kind of fits in with the other picture that we just drew. And while technically not correct, it's the best approximation that we can give without going way too complicated. The argumentation that we're going to use here is essentially the same as the ones that we used for the previous three. I need a new orbital. I pull the next available orbital down. And that would mean that I'm pulling down the d orbital in this case. So for steric number 5, the hybridization set that we are going to discuss is the sp3 hybridization. I've already pulled the S. I've already pulled 3 of the P's. That gives me 4 orbitals. To give me that 5th orbital to make the trigonal bipyramidal shape, I got to pull 1 from that D sublevel in that same energy level. For steric number of 6, I got to pull a second D orbital. We call that hybridization sp3d2 to give us 6 orbitals in total. And the net result is that octahedron shape. So these are just extensions of the previous hybridization arguments that we've already made. Like I said, we're kind of keeping a keep it simple, stupid approach to hybridization. The reality is, it is a good bit more complicated than this. But considering most of you are not chem majors or any kind of other major that would need to know the in-depth nature of molecular orbital theory, we're going to keep it simple. Hybridization we do know exists for the valence shell. The SP, the sp2, the sp3, those are all well-known, well-documented, well-accepted. And they fit into molecular orbital theory just fine. These two do not, but they're the simplest picture that we can provide to explain why the shapes are the way that they are, why the bond angles are the way that they are. So any questions here? So what does that look like? So again, where are we seeing this happen? Phosphorus pentafluoride. We've got a highly electronegative fluorine that is just anxious to bond, and it forces phosphorus into making another covalent bond. The 5 valence electrons in phosphorus through hybridization form 5 hybrid orbitals, each of which capable of making a single sigma bond. In sulfur hexafluoride, I've got 6 electrons in the sulfur atom. If I hybridize them into 6 hybrid orbitals, that would give me 6 unpaired electrons in those 6 hybrid orbitals to make 6 covalent sigma bonds. In summary, one of the things that I've been stressing for the past half hour or so has been the complementarity of what we've been doing the past couple of days with what we're talking about today. This table kind of puts that into perspective. Now, the wonderful thing about this table is it is part of your test materials for any Chapter 5 concept. So your Chapter 5 quiz, your second exam, this will be provided to you in some kind of form or fashion. But what I want you to look at is, again, to think about this in terms of complementary parts. SP hybridization gives me linear geometry, which puts them at 180 degrees apart. SP2 hybridization gives me trigonal planar geometry, which separates them at 120 degrees. SP3 hybridization gives me tetrahedral geometry, which dictates a bond angle of 109.5. SP3 dehybridization yields trigonal bipyramidal and gives me those 3 bond angles for the relationships between the axial and the equatorial positions. SP3D2 gives me octahedral, which gives me 90-degree angles and 180-degree angles. One other thing I want to point out here, I want to put a special highlight on our first 2 geometries. These orbitals here in blue, those are unhybridized orbitals. Those are your unhybridized p orbitals. And these are the ones that we would see that have capability for doing pi bonding if there were a double or a triple bond present. Pi bonding exists in unhybridized p orbitals in the molecule. So if we think about something like carbon dioxide, which has 2 double bonds in it, what we have in carbon dioxide, the linear shape, comes from that sp hybridization. The carbon forming sp hybrid orbitals to make a sigma bond to one oxygen and a sigma bond to the other oxygen. On the carbon side, what we also see, however, is that one of its sets of p orbitals links up with one of the sets of p orbitals in the one oxygen to make a pi bond to give that double bond on the left-hand side. A second set of p orbital interacts with another p orbital on the other oxygen to create the other pi bond to make the double bond on the other side of the molecule. When we see pi bonding, it is the result of those unhybridized orbitals interacting with each other. So since we brought up the subject, let's draw it out a little bit more firmly. Our Lewis structure for carbon dioxide looks as follows. Now, to evaluate the hybridization on any atom in any molecule, all that you have to do is count its steric number. So on the carbon, steric number is 2. It has 2 bonding groups and no lone pairs. It is sp. For the oxygens, my steric number is 3. I have the 1 bonding group to the carbon. I have 2 sets of electrons, 3 in total. sp2 is its hybridization, and it would be the same on the other side, since the bonding is exactly the same over there. And so what does that leave behind? Well, the carbon has 2 unhybridized p orbitals. Each of the oxygens have 1 unhybridized p orbital. So the bonding here, I have 2 sigma bonds, 1 to the carbon and oxygen on this side, 1 to the carbon and oxygen on this side, and I also have 2 pi bonds. All in all, 4 bonds in this molecule, 2 of them sigma, 2 of them pi. All right, questions with this example? All right. Oh, I'm sorry, Jaron.
So in the skill that we did on Thursday, when it asks for hybridization, asking for the atlas for hybridization of the molecule, asking for
In particular, it's asking for the center atom. So technically, we can determine the hybridization for any atom in any molecule. However, generally speaking, we're most interested in the hybridization on the center atom because that's what's going to dictate the shape of the molecule. But technically speaking, and that's where this gets really kind of interesting from that perspective, is all of these have shapes along the way. So the carbon dioxide molecule itself is a linear molecule. But if I look at the oxygen's electrons are actually arranged in a trigonal planar orientation because it's got those 2 lone pairs and the bond. And so to maximize its repulsion, it's going to put all 3 of those electron groups 120 degrees apart from each other. And so what we see is when we get into larger molecules that have multiple centers, individual hybridization on the center atom is going to be less and less important because we're going to look at, okay, well, this carbon here is sp3, it's a tetrahedral, and this one's sp3 and it's a tetrahedral, but the one next to it's actually only sp. And so the molecule itself is going to have a flat spot right here because it's linear there and tetrahedral everywhere else. Or one of the things that you had to draw in a previous, I think it was the Lewis structure skill builder, was a cis versus trans configuration with a double bond. Well, the double bond changes the configuration. Instead of being tetrahedral, now it's trigonal planar. There's a flatter spot there because now the bond angles are a little bit wider. And suddenly it becomes much more important how those two sides of the double bond are interacting with each other. Are the carbons on the same side of the double bond, or are they on opposite sides? The answer dictates a lot of what we know about the reactivity, a lot of what we know about its stability. Now, of course, that's more of a conversation for Dr. Peralta over in the organic, but it's a conversation we can begin down here because we can start to see how all of these atoms are interacting and what kind of a role they play. All right, let's do an example here. I've got selenium tetrafluoride. This is one that we've drawn now. This would be the third time. So answer this for yourselves. We've got a couple of minutes. What is the hybridization on the selenium? What is the hybridization on the fluorines? How many sigma bonds? How many pi bonds? While you're doing that, I'll walk around and kind of get everybody on the right page. And then we'll call it a week. We're looking at hybridizations. We need to look at how many electron groups are there for each one. So for selenium, I've got the 4 bonding groups plus this lone pair. Selenium has a steric number of 5, which would be sp3d. The fluorine, on the other hand, all 4 of the fluorines are the same. I've got the 1 bonding group. I've got the 3 lone pairs. That's going to give me a steric number of 4 in total. This would just be plain old sp3. And for fluorine, that's kind of its bread and butter. Fluorine, if it hybridizes at all, is going to hybridize in an sp3 kind of sense because it's already got 7 valence electrons. So adding the 1 bond gives it its 8th. You're already full. You're going to have all the orbitals there. Now, for sigma bonds, we want to know how many atoms are we bonded to? Because every single bond between one atom and another starts with a sigma bond. So in that case, I have 4 fluorines that are being bonded to. I've got 4 sigma bonds. For pi bonds, question is, do I have any extra bonds? Do I have any double bonds or triple bonds? because that's the only place I'm going to find a pi bond. In this case, all the bonds are single bonds. None of them, therefore, are pi bonds. Completely okay. Pi bonds are a rarity. Sigma bonds are a reality. So this concludes for us chapter 5. On Monday, we will start into chapter 6 and get into how do we apply all of these concepts from the past 2 weeks to actually talk about how molecules interact with each other. Have a good weekend.